Hey everybody, it's Dr. Brizendine. I wanted to take an opportunity to discuss American Fuzzy Lop with you, AFL. Is it the American Football League? No, it's not. It's actually a next generation fuzzer, state of the art coverage based fuzzer that achieves what it does through the use of instrumentation. Some advantages as to why we want to use AFL. Well, it can allow you to fuzz nonstop. As with other fuzzers, if you get it set up, get the CPUs going, crank that CPU up, maybe have dedicate 4 cores to it, or maybe you have a monster set up with 24 cores, let it fuzz for a period of hours or a period of days and see what can you find. It can also enable us to discover bugs that we might not find otherwise, some such as more difficult to discover UAFs. And one reason why it does that is because it's a coverage-based fuzzer. It's going to get in there and it's going to try to get inside every little path that it can and hammer it with input based on test cases until something, quote, interesting happens. Maybe something that is interesting could be a UAF. Because it is an evolutionary fuzzer, one thing that it does is it's very feedback oriented. So if it gets positive feedback, if we mutate and have hex opcodes at this particular byte position and we are able to get into a new code path, well, then we can use that to go further. And by doing that, it enables us to discover more code paths. More code paths can lead to greater opportunities for crashes. Ultimately, of course, we can use the results of this to discover bugs that we might otherwise miss. AFL is very well known for having scores and scores of bugs developed for many extremely well-known, well-used applications. If you go to the AFL website, they have a trophy case of sorts showcasing all the numerous things that bugs have been found for. Even major browsers. So many uses exist for it. So this slide really gets to the heart of the capabilities, the capacity of AFL. So let's work through what's going on here. This is a collection of JPEGs, all birthed from AFL fuzz. How did it do that? Well, they created a directory for test cases. It started out with hello, and they mutated off of that, and they took the feedback in terms of code coverage, in terms of paths discovered, to eventually generate legitimate JPEGs. So if it notes that it's able to get a little bit further in code coverage, if there's some particular opcodes that would be equivalent to the JPEG header structure, eventually AFL Fuzz was able to figure that out, which is really kind of amazing because it's not overly complex, but it's not trivial either. But it was able to do enough mutations and to make use of that feedback to actually generate legitimate JPEGs. So just off of hello is the only test case. Think of what it can do with actual real test cases. So let's learn a little bit more about AFL, some background. Altkamptough is the developer, is a Google developer. And it goes back to about 2012, 2013. A couple of different ways in which you can approach AFL is one is to make use of the source code. If we have the source code, we can compile it so that it has instrumentation. So if it has instrumentation, then that allows us to allows AFL to much more easily be able to discover new code paths. And as we get down these new code paths and we enhance the code coverage of a binary, that just increases the chances, increases the odds that we could reach a crash. Because ultimately, any fuzzer, our goal is to generate crashes. So, more paths, more opportunities. Now, that said, of course, if you want to get more crashes and want to discover more paths, enhance your code coverage, you want to let it fuzz as much as possible. Let it go continuously. Maybe several hours, maybe a day, maybe a few days. Maybe throw more CPUs to it. You can do it in parallel, you can do it distributed. So, as I alluded to before, AFL takes advantage of the concept of evolutionary fuzzing, or you could call it instrumentation-guided fuzzing. Now, it's evolutionary in terms of the input that it generates. So we can feed it test cases. Maybe we start out with a JPEG parser, we feed it 5 JPEGs. Okay. Well, eventually it's going to discover and create JPEGs of its own. Some of them may be valid, some of them may not be. But if it allows it to discover new paths, then those are things that are interesting and they could potentially be actual test cases. So that will go into our output. So AFL can allow us to generate new, more relevant input to use for the fuzzing, and it uses the feedback from the control flow in terms of the different paths that it goes to reach more locations in the code. If we can reach more locations in the code, that means there are more things that we can fuzz. If there are more things that we can fuzz, that means there are more places where we could potentially get a crash. Because, again, we are after crashes. Now, we could have 100 crashes, but maybe it's only 3 or 4 unique crashes. We're not concerned with the volume of the repetition of the same type of crash stemming from the same issue, the same area. We're more interested in the unique crashes. And AFL can take care of that and identify those for us. Now, AFL is nice. It's very quick and easy to set up. You don't need to have extensive background knowledge of the data that's being parsed. You don't need to be an expert in JPEG format or GIF format or go do extensive research on that. There are other ways that you can go about doing that. You can get a good corpus of test cases, known JPEGs, and make use of those. Evolutionary fuzzing is also great because it can eventually allow us to reach some of those difficult to reach code blocks that might be much more challenging to do through more traditional fuzzers. Now, evolutionary fuzzing can use a lot of CPU. It can use as much as you can give it, but it makes good use of that CPU, I promise you, because it can give us some absolutely terrific results. So again, it's a coverage-based fuzzer. Now, what we will be doing is we'll be working with source. Now, you can also do it without a source, but that's not something that we will be addressing today, except very, very briefly. So if you want to do it without source, you can make use of QEMU, and that allows you to do a black box approach. You just have the binary, you don't have the source code. It's not going to be as efficient. It's not going to work as well. It's not going to be as fast, but it's still possible. That said, if you have the source, it's going to be a lot easier and a lot faster, a lot more efficient. And we care about efficiency because, again, fuzzing can take a lot of time. It could be days, it could be weeks. If it's very substantial, it could go on beyond even that. So we need to be very smart about how we do that. Take advantage of every possibility. So having that instrumentation uh, embedded in the compiled binary to help us out is something we definitely want to do. And other things that we can do to increase the efficiency, which we'll talk about in some other slides. Now, when you start AFL up, it should be able to find new code paths almost right away. At the very worst, maybe within several minutes. If it's giving you problems and you're not finding anything, it'll give you a message and say, not able to find anything. It'll be in red. And that's indicative of problems. So if that's the case, you probably want to stop it and figure out what's causing that. Maybe the syntax is wrong. Maybe you're missing a test case. It's hard to say, but it's something that needs to be investigated. There could also be memory issues at play. So if it just demands a ton of memory and you're not giving it enough memory, well, AFL doesn't have enough memory to do its thing, so you may need to increase that. Maybe you're working on a system that is very low memory. But, I mean, that's not ideal, but as a student, you may not have a system that's built for AFL, so you just may need to deal with that, I guess. Input files could be invalid. Maybe they're not passing a simple header check inside of the software being fuzzed. Now, if you get AFL to work, then the throughput can be much, much faster, much, much more efficient than a traditional fuzzer. So you can blaze through things that would take much longer otherwise. Some great targets for us. Image parsers, JPEG, GIF, any of those types of things. We can have a nice, strong corpus of test cases. Compilers, browsers, compression utilities, network services, shells. All of those are very well susceptible to being fuzzed. Some of them are a little bit more tricky. Image parser is one that is very simple. The nice thing about AFL is it's relatively simple to set up, to get it going. It's more so than something more complicated in Peach, which really the learning curve on that can grow quite a bit. Now that said, if you want to get things set up in AFL, you can be very, very simple. But if you stay at the very, very simple level and don't go a teeny bit beyond that to the maybe, intermediate level, then your ability to discover actual real crashes is going to diminish greatly. So some of the things that we'll be talking about today, you want to pay attention and do those, or you might not find any crashes. And we'll talk about these things as we continue on. So open source, if you have big, nasty, ugly code, that's fine. AFL can handle it. A great example of that is code that might have 6, 7 if statements, nested if statements. AFL can go on and penetrate those, and it can get into those much more easily than other types of parsers. And there have been studies, informal studies done, just showing the efficiency of AFL to approach something just like that compared to a more traditional fuzzer, and it really is light years ahead. AFL has successfully found numerous bugs by fuzzing many major applications, finding some very hard to find bugs in C and C++. Now, if you're going to get really, really serious about this, and some people do get very serious about it, you want to devote a lot of CPU to it, and give it as much RAM as you can. Maybe you get a 24-core machine. Doing it in the cloud doesn't always scale all that well, but there is also the possibility, if you don't have those actual machines in your home or office, you could rent use of physical machines that you could do remotely. So that's a consideration. Um, but doing it in the cloud just does not scale as well, just because it would be consuming large amounts of CPU for very long periods of time, which they don't really like too much and doesn't really work out too well. Now, AFL does add instrumentation code, as I alluded to, and the reason for that is so it can monitor the execution path. So with that instrumentation, it's able to discover if they find new paths. We can use that to help build our memory bitmap, so that we can figure out, and we have a map of it, and we can use that as a way to discover things and indicate whether or not they're considered interesting or promising. Again, it uses feedback to allow us to get better coverage. We're able to look at the binary that's running. If we see something that's hit, it's successful, it's able to gain additional code coverage, go discover a new path, then we can make note of that. We can mutate the input and see if, once we've mutated that input, does that allow us to discover a new code path. And we just hammer it with repeated different mutations of input. Get from point A to Z, and along the way we stop at point F, and we've gone through a series of mutations to allow us to do so, and we want to see if we can get further. AFL is also smart, so it can determine if it just keeps on doing the same thing over and over again, which is just a waste of its energy. We want to be more efficient about this and to gain greater code coverage, try to gain crashes. Now, AFL is a little bit, well, just the nature of using feedback in and of itself is going to be slower than not using it, but because we do use the feedback, then we can bypass certain things. We can avoid repetition, and so overall the results are going to be much superior in the long run. So more efficient. So in the short term, actually using instrumented code is going to be a little bit slower, but it is much more advantageous for us. Again, the best results are if we utilize source code and compile it with AFL and allow us to get the instrumentation. So how do we install it? Now I will provide this in the IA lab for you. I haven't done so yet, but I'll get to it. And so we just do, but if you want to do your own setup, then I would encourage you to do so. For this particular lab, you may need to have it running for a period of time. It could be several hours, could be a day or two. So make sure it's just set up where that is appropriate, where you can allow something to run continuously for a period of time. If you think that's going to be an issue, you might think about the IA lab. That is a possibility. So we just go there to Alcamptoff's site and grab it. tar xzf will unzip it, and then we go to the directory and we do make and then make install. And these may need to be separate. You may need to do a sudo on make install. So finding something to target, what do we want to target? Now, ideally, again, we want to instrument it. So we want the source code. So GitHub is a good option. If we can maybe find something on GitHub, then that could be something that we could make use of. We can use AFL to modify it, so that when we compile it, we're using AFL GC. So in order to do that, I'll show you what to do later on. But so overall workflow here is we want to compile the binary with AFL. So we find a project that is of interest to us, and we go and we instrument it by compiling it with AFL. Now there's also the possibility that you could use an existing binary. That's again a black box approach, but it's not something that we'll be discussing in today's lecture. But that is definitely possible. You also want to establish a test corpus. What is your input? If it's a JPEG parser, it needs to parse JPEGs. Do we just go to Facebook and grab the first JPEG? No, that's probably not a good test case. If you have a GitHub and it's something with actual sophistication, then there will be existing test cases, and so you might use some of that to form your corpus, things that you can test your input on. If it's something like a JPEG or bitmap, maybe you might go and do research and find a website that is in charge of the JPEG specification. There's a good possibility that they would provide a corpus of files that you can make use of for testing purposes for people that build JPEG parsers. Because when you create something that parses a JPEG file, it needs to be able to parse and read and understand that file, and so it needs to have things that are done differently. Files that may be doing obscure, weird, unusual things, but that are still very possible and that fall into the parameters of what is defined by the JPEG specification. So a good parser should test for all of that, not just the very simple, obvious, run-of-the-mill type JPEGs. So a good test corpus is very important. And as we'll see in coming slides, we can also develop and improve our corpus too. That's one thing that AFL will do, is it'll generate additional new input that it discovers. And then we run the fuzzer, and we can triage our findings. So this is a very basic and simplistic approach to fuzzing with AFL. I have another slide later on that goes a little bit more complex, but for right now, this is maybe a good starting point. Triaging is analysis. What is the cause of it? So with Peach, we saw that we'd make use of exploitable with WinDebug, and that could tell us, give us some output, a starting point, if you will. There's an exploitable extension for GDB that you can use. GDB could be something you could utilize for triaging. I'm not going to require triaging for this because we're not going to delve too much into Linux. So compiling, different flavors that are available: GCC, CClang fast. So how to do this? When you get to the directory of the make file, you just simply type on the in terminal cc equals and then the AFL compiler and then make. Now that would be ideal if that's all that was. The reality is a lot of these projects will utilize make files. The make files may be sometimes complex. Now inside a make file, they might have CC, but they might also have GCC. So in this case, you would need to go in there and physically change the hard-coded GCC to AFL GCC. So we want to pay careful attention to that. There's another option as well, AFL hardened. We don't talk about this too much. This is really the only mention of it actually. But that's another option if you want to try to cause crashes more quickly. You can add some additional things like stat canaries. It could potentially lead to some false positives. But when we get to the triaging stage and you test these on a non-AFL instrumented binary, you can see if that really is a relevant crash or if it's a false positive. A false positive being something that, AFL could generate a crash, but it could be for other issues. It could be maybe there's not enough memory, so it crashes. But in the actual binary, there's plenty of memory, and it would never crash. So that's an irrelevant, useless crash. In the same context, AFL harden potentially could cause some other crashes that may not be too terribly realistic. On the other hand, it could allow us to find some more quickly that might not otherwise be found, or that might be found much more slowly. So finding a test corpus, potential sources, again, we could look to the source code. If the source, wherever we get the source code, whether it's from GitHub or who knows where, if it's a more advanced, sophisticated piece of software, they should have some test cases, things that they test it to run it with, inputs to see if it functions smoothly without problems. If there are not test cases, then it's probably pretty small time, which is fine. We could still, there's no reason we can't do those. It just means that we need to look elsewhere for our potential sources. And actually, if they don't have test cases, and you suspect they haven't used test cases, then there's probably a greater probability that there is potential software vulnerabilities that we can make use of. So don't necessarily look for it as being a bad thing. AFL does also provide some minimal test cases, and I mentioned some other sources online. Don't be afraid to do a little research online to search for relevant test cases. If you're parsing a particular image format or movie format, there are places online that act as repositories for those file formats. So feel free to check them out. Minimization, we want to speed things up. Two big things we're concerned with is CPU and time. If we can make the time that one fuzzing takes shorter, well, then we're going to get much better throughput. We can find results faster. So we do minimization. We do minimization in two different ways. I have this in opposite order, but firstly, we want to minimize each test case. So if I have a JPEG, specific JPEG, I want to minimize it and make it as small as possible, remove any extra bytes. And that may seem trivial, but it all adds up. And that's part of why AFL can be so fast, because it deals with minimization in many, many respects. So we take our test case, we let AFL minimize it, and as we grow, as we're fuzzing and our inputs grow, which if you're doing it correctly, your inputs will grow, then we may get a large number of test cases, and that can take more time. Some of them is going to be very repetitious. They add nothing. So if we can eliminate them, then that is great. And unfortunately, we can eliminate them and minimize the number of test cases. So AFL T-min and AFL C-min is what we would use in those steps. So we see the syntax there. Test case file. Well, this is an actual specific file for our input and our output. Actual specific file. The binary we're going to run, and then the options. And you may use this as well for an item that may be fuzzed. So we see it being run right here in this instance, actual real world input that you could utilize. Our inputs, actually this is incorrect. So we'll just call this one.jpg, and output is maybe I min. Okay, I min because we're minimizing it. JPEG. So that goes there and that goes there. So this is not a directory. These are specific files there. So let's just minimize it as much as possible so that we can get more CPU. And if I can figure out how to, I don't know how to get rid of that. Let me just do this. Okay, so next step is, well, I guess it's a continuation. So we want it as fast as possible. So AFL CMIN, we minify test cases, and AFL TMIN, we do minification of the test cases. And I provide examples here, and again, this one is specific file. These ones are actual directories. Now this one we notice here is Q. So when we O, that originally was an output folder. The output folder can also create a queue of things that are going to be coming up next to be fuzzed. And within the queue, we can have other test cases that it creates. So we can go in there and we can make use of those test cases that AFL had discovered for us. They didn't previously exist, but AFL went and found them for us. And we can minify it and we output it to a new folder. So a new output, input 2. So maybe we'll stop AFL and run it again with a brand new input. So we have a file that's being fuzzed. This is not an actual file, so I could call this whatever I want. And then the source JPEG, so JPEG is the file name, or the binary name. And the source is just, we're just getting to the directory where it's located. And then right here we have the same file. Another trick you can do is you can isolate the code that you want to fuzz. So maybe you just want to do a small image parsing from a much larger software. And you can extract that out. Maybe write a wrapper around it, and there's also a loop that I'll show you in another slide that you can make use of. But ultimately, again, speed. We want things to go as fast as possible. If we go faster, that means we're going to get the crashes much faster. If we have giant, huge images and repetitious test cases that are the same thing but just different, and I don't mean literally, of course, but it's not adding anything new to the mix, then it's going to slow us down. So we wanted to get rid of all that excess. So how do we actually run it? Well, towards the end of the video, we'll see how we actually run it. But let's talk about the syntax now. So AFL fuzz, and then we do our I for input, our test cases, and then the O for our output, so it can generate more test cases for us. And then our fuzzing option, there are a number of different things that you can make use of. Binary to run, options to the binary. So we'll path out the binary, and then the options, maybe we're feeding it a specific file, for instance. So my input, my output, I'm running it there. Now we can also do this in parallel. And so if you're actually getting really serious about this, then that's probably the best thing to do, because running it in parallel means if you have 4 cores of CPU, then you can use all 4 instead of 1. So maybe you're 4 times as fast, or it may not be exactly 4 times as fast, but it'll be faster than what it would have been otherwise. So we do that because we're smart, right? We have a master. The master is the one that is deterministic. And these ones here are non-deterministic. This one's going to be slower, but it goes and discovers the new paths. And then we got our slaves, little fast guys that are, going on existing coverage, trying to cause crashes. Now, memory sometimes can be an issue, depending on the binary, what it's doing, stuff that AFL is doing. So if you need more memory, you can increase that. That is an option. So we can do the -m option. There's another option too, so that if you really want to do unlimited memory, you can do that. Sometimes that can be problematic though, because some things can be memory hogs and it'll just be extremely excessive. And you could run into some issues there. So for efficiency, it's usually good to use a max memory unless there's a specific reason not to. Now, there's also the option for timeouts. So if something times out, then that's considered a hang. And that's a good thing, because do we want it to get to a code path where it's looking for a specific checksum, and do we want to calculate every possible combination until it gets the right exact checksum or some password or something of that nature, that eventually, if you brute force something, you'll find it, but it could take a monstrously long time. That's not what this fuzzer is about. So if it's something like that that takes a lot of time, we nope out of it. We're not concerned with those types of issues. That's not what this is looking for. So when it does outputs, it'll generate outputs in a number of different ways, providing an output folder for each master and all slaves. That is if you do use master and slaves. Now, for you guys' lab, do you need to use a master and slave? No. In fact, I'd recommend you don't, just to make it more simple. If you feel you really understand it, great, go ahead and use it. After all, the more you do, then the better your results, the higher the efficiency. Ultimately, it's a matter of hardware and resources, CPU, as well as RAM. So memory and speed. Crashes will be the folder where we actually get the crashes that cause, or the inputs that cause the apps to crash. Now again, we could have 100 crashes, but only a few of them may be unique. Whatever the case, we'll have our crashes will go into the crashes folder. And so when we want to go in triage, that's what we're interested in. We're interested in our crashes. The hangs will be input that causes something to get stuck. The queue is going to have our synthesized corpus. So we could take that synthesized corpus and we could rebuild off of that. I'll talk more about that a little bit later on, but let's start thinking about that. It contains the original files as well as the test cases for each path. So triaging, we've alluded to this a number of times already. So when we get to the triage stage, at this point we've been dealing with an instrumented version of the binary that we compiled with AFL. Now, when we have the triage, we have something that caused an actual crash. We want to see how it works outside of AFL. And so we have the regular binary, no AFL instrumentation. We run it with the input, and we see if we generate a crash. Now we can use GDB, and there's a plugin of sorts called Exploitable, a different Exploitable, that we can use to analyze it and to get some feedback for us. Is it exploitable? Is it not exploitable? Can we capture bits and pieces of CPU, memory state, stack trace, those sorts of things, so that if we look at it, we can see, okay, this is a null dereference, we're looking at uninitialized memory, this is stack buffer overflow, this is exploitable, this is not exploitable. And then from there, we can decide if this is something that is maybe useful to us. We could take a closer look at something. Is this a real vulnerability? Did we discover a real vulnerability? Or is it something that's not useful to us? Maybe it just ran out of memory. So AFL also has a script to not hello, but to help. And that's in the experimental directory under crash triage. It's called crash, or triage is crash.sh. So we could go there, use that script, and do much of what I described previously. And of course, GDB is an option, and we can import that inside of GDB and make use of it, and that'll classify it and let us know, hey, I'm exploitable, I'm not exploitable. So let's try to understand how we can make a better understanding of crash files. So these are actual inputs that cause a crash. And they're named in a very bizarre looking way, but it's actually a very bright way of doing it because it embodies all the information and it's all right there in the file name. So it has distinct IDs. The SIG will tell us what caused the SIG fault. Is it signal 6, which could indicate out of memory issues. So different signals, we could look those up. Source, the parent path to the source. So we could go to the queue and find a file with that ID number and see, how does the original test case differ from the fuzz file that caused the crash. So we have an original one and then a fuzzed one. What's different? What do they do that's different? We could check that out, analyze that. If it's something that proves promising, we've already gone past the initial triage stage and we decided, I'm going to take a deeper look at this. The fuzzing strategy, what are they doing? Are they flipping bits? Are they flipping bytes? So different strategies that might be useful to us, might not be. And then specifically the fuzz bytes. Where in the file is the flipping operation being done? Well, it's been done at position 60. So we might, analyze, I'm in position 60 and this input, how does that come into play in terms of things like structure? If we map this out as a JPEG, we mapped it out and looked at the structure, what does that mean? Which attribute is it? What am I doing that's different? It's not just a random chunk of binary blob. Position 60, we open that up in something like 010, we map out the structure, we could see where position 60 is. And that's where we flipped it, and we did something to it, and it caused a crash. So it's at that specific location. So we have our crash input, and we can also go back and visit to the initial test case. Maybe figure out all this helps us is figure out what we did that was different to cause that to happen. So very useful information. Now sanitizers can be another option to use at the triage stage. So we don't do this before the triage stage, but when we are triaging something, then this can allow us to dig a little bit deeper. So we have inputs that on the instrumented binary, as well as the native, the original binary, cause us to get a crash. So we want to investigate it a little bit further, and what this does is it replaces malloc and does a little bit of some changes so that if there is a memory issue in play, it's going to draw it out. So whenever there's memory at issue, it'll just rearrange the memory so that if you just even go, 1 or 2 beyond wherever it is, you're going to cause that. It's kind of a vague, general way of approaching it. I would recommend checking out the address sanitizer page. That does go more in depth, but it does allow us to draw out many categories of memory issues like use after free, heap buffer overflow, stack buffer overflow, and others additionally that are maybe more pertinent to the Linux environment. So this is built into some modern binaries or compilers like GCC, and so you can use this switch to make use of that if you so desire. So I would encourage you to check that out for the triaging stage if you're trying to maybe figure out is something potentially relevant for memory issues, heap overflowed. Something could be relevant for heap issues or other memory types of issues, but you may need to have very special input, which you could go through, iterate through the development cycle and find that out. But this artificially makes it as easy as it can be. So if you're just even one off, it'll be there to catch that in that memory issue. So it makes it really very easy. So some compiler options there if you're going to now this is a compile option if you're going to do it with AFL. A lot of times it's probably maybe not the best to do it directly with AFL, but that is an option. If you are going to do it with AFL, then you probably want to readjust it and do it 13-bit. So that means compiling the binary, the target binary is a 32-bit binary. And I don't expect you to do this for your lab. This is additional information, so this course provides you with a good understanding, so that if you actually want to get serious and do this for real, then you have the knowledge and tools to do this. So we would want to recompile our target binary as 32-bit so we don't run into memory issues, and some commands there to maybe figure out how to do this exactly. So we may need to go and add the i386 architecture, 32-bit. When we do our GCC, we'll need to do the -M32 switch to compile it as 32-bit. We may need to change the dependencies when we compile that. It may need different dependencies. It's not 64-bit now. If it's using 64-bit dependencies, that's a problem. So this command, the apt get build dep, and then the binary name, and then colon i386 or 8664, will go and build the dependencies for us. So it'll go out there and try to capture all those dependencies for us. We can also do the apt cache show, the binary name, and it'll show us the requirements for the dependencies. And speaking of dependencies, that's also something good to be cognizant of when we're thinking of what we might fuzz. If it's something that is very complicated with many dependencies, I mean, you can still do it. There's no problem with that. It just adds sometimes a little bit more complexity, and the speed may not be quite as fast. Now that said, there can be different approaches to something like fuzzing with AFL. One approach could be is maybe you're a hobbyist, you're just trying to find some vulnerabilities, you don't necessarily care where the vulnerabilities are, but you just want to find a software vulnerability that could be a CVE, or may not even rise to the level of a CVE, but just want an actual vulnerability. So you're not necessarily too picky. The other approach could be you have very real specific targets. Maybe you see $signs in your mind when you look at things like Chrome or Internet Explorer, and you want to do some fuzzing on some very much more relevant software rather than random obscure pieces of software that they may be vulnerable, but they're not very widely used, so the overall impact is going to be much less. The value of them is going to be much less. So in those cases, I mean, if dependencies, it just really depends on how much your approach is. If you have a very specific target, then it's going to take whatever time it's going to take, and you can do things to help minimize that, but it still may take a long time. We can also specify the memory that's being used, so if we need more memory, then we can enhance that. So AFL usage, we do the AFL, we do our input, and we path that out to a folder. The output, we path that out to a directory. In this case, we're doing cat, so that's what we're doing. And then the @sign is a placeholder for a fuzzed input file, so we could provide that. Now this is a more detailed, well thought approach to the process. So initially we find a program to fuzz. Um, Ideally, for us, we're going to be using the source code to create an instrumented binary. Out in the real world, you don't have to do that. You can do a black box approach. Just adds more steps, a little bit more complication, not quite as fast. We need to find or develop a corpus. Well, even if you find one, you're going to want to develop and refine it to utilize. If you just start AFL, fire it on, and do nothing and let it run for several days, you might not find anything. You might not get any crashes. Okay? We need to refine and develop what we find in order to be successful. So a few tricks that we can make use of. One of those is we can create a relevant dictionary. These are things that are going to be relevant to whatever it is that we're fuzzing. If it's a JPEG, specific things that are relevant. We can use the AFL tmin on our test cases. That'll go through and minimize a test case. And then once after something has done a complete cycle, then we can stop it and we can run AFL cmin to minimize the corpus of different test cases. If there are certain test cases that are unnecessary because they're repetitious, we can remove them. And that's what cmin will do for us. Now again, cmin just runs on one specific file. So if we're doing that over a large body of files, which we will be, we need to come up with a bash script to take care of that for us. Because ain't nobody got time to sit there and run AFL cmin on 1,000 test cases over hours and hours, right? I didn't think so. And then repeat and refine. So we use we develop our test case, we develop our dictionary, we run tmin on our corpus, we let it run, we get some actual input being generated in the queue. We can go there, we can grab that, we can run cmin on it, and after we run cmin on it, why not run tmin on it? Because initially we ran AFL tmin on the original corpus, not the synthetic corpus that we generated. So we could apply the tmin to that and reduce it even further. And then let it go, let it run. Maybe a cycle later, we might take another look and do that again. Why do we do that? Because it speeds things up, makes it more fast, more efficient. If we didn't do that, it would eventually get to everything. It just would be much longer. And in the case of the dictionary, that really does enhance things quite a bit. And there's some other tricks with the dictionary that we'll talk about in a future slide. And when do you stop? Now that can be kind of an art to some extent. You want to, ideally the goal is to get unique crashes. If you're not getting crashes, then that's really a problem. You're not doing enough. We need to get crashes, and unique crashes moreover. So we've got to let it go at least a few cycles. We have to engage in the process of refining our corpus, making use of a dictionary. But eventually, we're not going to find any more crashes. So, one way we could find more crashes is maybe we discover a new path. A new path leads us to something that maybe there's a memory corruption bug there that we weren't able to, well, that wasn't accessible to us. But now, because we found this new path, we can access that and we can feed it an input, and that input causes a crash. We're using the same inputs all throughout. There could be, maybe we have 500 inputs, and that input is going to eventually go through every path. Um, but does it need to necessarily? No. And so AFL is fairly it's a smart fuzzer. It's smart about how its approach to that. Very deadly efficient. So we don't necessarily need. I mean, we could let it run forever, and it could keep going on through more and more cycles, and eventually it may find something. But at some point, I mean, you found all that you are going to find with that particular corpus. So you may need to give up. I mean, other things you could do. I mean, maybe you could find something relevant to expand the dictionary. Um, I mean, that could be a manual process. You could feed it a file with things that you think are relevant to whatever it is that's um, being fuzzed. Or maybe you find some other good test cases that are completely different than the existing ones. So some other commands. We got AFL, got CPU that lets you know how many cores you have available. So maybe it's something, a machine that you rented online, or you're doing something in a virtualized environment, and you're just not sure the CPU cores that are available, or even it's your home machine and you just don't know. That tells you the information. So you can see if you want to do parallel fuzzing and how many cores you can devote to that. Screen. Um, that's kind of a trivial comment there. But you can actually use screen so that if you have something running in terminal and it's fuzzing for hours or days, you can set it up so you don't accidentally close the screen and lose your work. So I would investigate that screen if you want to get serious about that. AFL what's up, you can run that on output directory, and that lets you know in different output summaries. So we see image here. Overall cycles done 0, so it just started out. Total paths over 4,000. 0 crashes, 0 hangs. So this is very early on. Map density and coverage kind of low. Some information on findings there. 0 crashes. We got some timeouts. We can go over here to our progress section. So the speed here, 900 a second. We want this to be as fast as possible so we can do things like minimization. That can help us, definitely. These can get into the 4,000, the 5,000, depending on what it is you're looking at. If it drops very, very low, then you probably want to stop, and you probably have it set it up incorrectly. There may be some issue at play, so you may need to stop and think about it, investigate. But that said, depending on your machine, maybe it's in a VM and you're not giving it as many resources. You have other things going on. Maybe you only get 900, and somebody else gets 5,000. I mean, it's still a big difference in CPU execution speed, but that's also much more different than, say, 900 versus 300. So if it gets really low, that's probably something to be concerned with. So status indicators, favored paths, gives some information there. Last new path. Execution speed, again, ideally several hundred or over 1,000, maybe 4,000, 5,000. It really depends also on what it is. If it's a very huge, massive, non-lightweight program, it just may not be that fast, and you just may need to deal with it. The map coverage will let you know how your fuzzy and bitmaps are how they're filling up. Some of the things there to be concerned with. I mean, if you're getting really serious about that, then you need to be aware of things like this. Path geometry. Let's skip over that. Cycle done tells us that it's been through all of the paths that it has found. Does it mean it's every path? Well, no, it may not have found every path, but it's gone through every path that it has found. Overall, you should let it fuzz through at least a few cycles. But as I mentioned before, it's often a good idea to maybe stop and refine things, and that can allow it to run better. If you start out with two test cases and you eventually develop more stuff, well, make use of that knowledge. Hangs will be unique code that goes beyond a specified timeout. How many different unique paths have been found? So we found over 4,000. Number of crashes, and those are the number of paths that lead to a crash. Some evil things to watch out for out of memory crashes. Again, I mentioned AFL can artificially limit some of that, so there could be a crash that is artificial, but when you get to the actual real binary, it's not relevant because it's all AFL. So we don't care about those necessarily. If it's a slow binary, well, that sucks. It's slow. What can we do to speed it up? Maybe we can do something. Maybe we can't. Again, I talked about the different selection of different targets, why we fuzz. So that may be relevant, may not be relevant. A big test corpus. Bigger isn't always better, so start small. Minimize as much as possible. The same thing with the test cases. If some specific test case is too big, then make it smaller. Well, you'll be much better off for it. Other optimizations, we've talked about this before, but we can do parallel fuzzing, so that'll enhance things. Now again, you're not required to do that for this lab that you'll have on Thursday, but you can if you want. If you do that, you'll need to do some additional research. You'll need to have a sync directory. So we haven't discussed everything what the info mission is out there. And then distributed fuzzing, so instead of multiple CPUs, you can have multiple machines. Some things you could do, LLV mode, instead of writing something to assembly and then rewriting the assembly, you could also use AFL AS to write true compiler instrumentation. And by doing that, you can make use of compiler optimizations that wouldn't be otherwise available. AFL's CLang fast, just faster, so that'll maybe speed things up a little bit. Deferred instrumentation is another option. That's a more advanced topic that I'll let you check that out more on your own. Now, we can also help speed things up and maximize our efficiency by making use of the optimization where we could establish a starting point. So we could do that. So if there's a big convoluted time-consuming initialization sequence, we can bypass that. So if we have the actual source code, then we can do this right here. So that'll let us know AFL to start there. So something you can do there. Persistent mode, if you have an application that takes a really long time to start up, maybe there's a small section that you want to test, but you have no other way to isolate it. So what you could do is you could loop over a particular code target many times without having to waste resources. So in this state, maybe we're dealing with something like parsing a JPEG. We're reading an input. Maybe we're reading some JPEG. It's going to call the library and do something on the fuzz JPEG. So we'll let it go there, read this JPEG, and then it'll somehow reset the state or clean up, which, I mean, you need that to be in there because it needs to be restored so there's no JPEG. But that way, if you have, say, a large number of JPEGs to go through, or even a small number of JPEGs, but exploring different paths, then you just keep focusing on this area of code rather than having to do all the initialization. So that can speed things up, be a little bit more efficient. We'll bypass this one. So dictionaries. So they can be directory of files or a single file with key value pairs. There's a good link there to check that out. So if you use something that's known, then that's great. Then you don't have to discover that on your own. It can maybe make things a little bit faster by adding tokens and other structures that may be common. So MPEG-4, maybe you scrape out all atom names and place them in a directory. That's cool. We could also take user-supplied values from dictionaries and place them in. So if you really do have a good dictionary, then that can really speed things up. And the reason why is if you don't, then, I mean, like our JPEG example early on, eventually it can discover and find the syntax of a file format that you're fuzzing. But if you can make it easier for it, you can speed it up, why not? So that, I mean, 8.7a, that's something that needs to be in a GIF header. A legitimate GIF. So if you're fuzzing a GIF, help it out and include that so it knows to maybe make use of that. One other trick that you could do is, and we'll show you later on in our little demo here, and if you go to the readings, you can actually get the code off of the GitHub, is we go and take all the constants and all the strings in a binary and we add them to a dictionary. If it's in the actual binary itself, there's a much greater likelihood that it could be relevant. So scrape it out and make use of it. So that's what we do. We can add to our dictionary ourselves. So that's pretty cool with the dictionary. Checksums. Now this is something that you really want to avoid. So if there's a part of the code that's you need to generate a checksum to advance forward, a unique checksum that could vary. It's going to be pretty difficult to get a match on that, for it just to come up on that. I mean, it could, but it's probably not going to. So if we want to comment out checksum verification code, well, we can do that. It just makes it a little bit easier so that we don't have to waste CPU on that. So right here, this is a good example on how we could eventually use AFL to help us bypass ASL, address space layout randomization, on browsers. So in this example, we're using it on Internet Explorer to try and find an information disclosure, the information disclosure being maybe memory address of a function that's on the stack, and from there we could deduce the base address, and thus we have the base address. That tells us if we have the base address, then we can find any other function that belongs in that DLL. So that can be very, very powerful. If we can have an ASLR bypass, that opens up exploitation to us tremendously. So if you don't know what ASLR is right now, don't worry about it. We'll talk about that more later on. So how do we do this? How do we start that? We could start with an open source image parser, maybe generate a synthesized corpus from it, go into the queue from the outputs, see what it generates. Get some HTML and JavaScript from AFL source, iterate through all the test files and the test corpus, load the iframe content to populate the memory with data, create an HTML canvas, and then once we've done that with JavaScript, sorry, I got lost in thought. With JavaScript, we can keep loading the graphic, rendering it to the canvas, say 50 times. Meanwhile, we can be comparing the image data, looking for changes. If output is non-deterministic, meaning something sometimes it's using data from place A, place B, place C, then potentially, and maybe you making use of uninitialized data, which potentially might mean that it could be something on the stack. If it's something on the stack, then maybe it could be a function address that's on the stack. And then that could be our ASLR bypass, a memory disclosure. So, I kind of glossed over that quite a bit very quickly. But ultimately, that the workflow ultimately could, if you got lucky enough and found the right vulnerability, then that could lead maybe to an ASLR bypass on a browser. So just one example of the power there. Of course, AFL can discover all types of vulnerabilities, so the vulnerabilities really is limitless in terms of what it could be and what it could do. So AFL Unicorn, we're not going to talk about this, but this really just gives you more information on the idea that you can fuzz non-standard devices, and you use Unicorn Engine to do that, to help you out. So if we do that, then we can, it opens up some other possibilities, but I think we'll skip that. And with that, we'll get into our little demo. So right here I have a starting point, and I'm going to extract it. So this is the binary right here, JPEG, and there's build script. We could look at that. So we see the G flag is there, so on and so forth, but also a source directory. So we could go into source. There's a make file. So I see pretty simple. And then the additional source content here. So all these C files that it'll need to compile, and then a make file additionally. So let's take a look at that make file. So right here I see hard-coded GCC. That is something that will need to be changed because we need to compile it. And then the CC, those will be taken care of naturally. So I save that, and so I can do CC. And make that AFL GC, and then make. And so now it's going through and making it with AFL instrumentation. I know it's telling me that it's being instrumented, and so we'll just have to wait for it to do that. I don't have any error messages, so this looks like it was successful. And I see the JPEG here, so that's the name of the program. You guys can move closer if you need to see the screen better, feel free. So we can look into the input there. I see a couple JPEGs. And then let's try to run it. So JPEG, and then let's logo. And I'm making some mistake, probably very trivial mistake.
You mean in the run JPEG?
What?
Are you meaning to run JPEG?
There you go. So checksum there, so it works. That's all it does. And so we want to fuzz it. And so we have test cases. Now, well, let's just go ahead and run it without the test case. So I'm in the directory for AFL. I'm going to do AFL fuzz. And then I go to the JPEG, and first I want to do the input, so it's going to be inputs. That's the folder where my inputs are, and then I forgot to do make. So make a directory for the output. Oh, it already exists? Okay. Well, I guess that's convenient. Oh, I'm in the... That's why. So do our output, and then do in class JPEG, and then output. And when we do a file, I'm just going to call it file.jpg. It's a file that does not currently exist. And then I need to get the location of the file. So that would be in class JPEG, and then source. Then JPEG, and then I'm doing file JPEG on it, and I think this is correct. And so it's starting up. Now, when you do this the first time, it'll give you a message about CPU caching. There'll be a little thing it'll show you what to do. Just simply copy and paste it, and once you do that, then it won't allow you to get to the screen until you do that, but it's pretty straightforward. So we let this run for a little bit. We see it's discovered 25 paths. We see the time there, map density, count coverage. So we're pretty low. So we found 0 crashes. Our speed is... It's not great. I think it's just restricted here because of the VM environment. And down here you can monitor CPU utilization as well. So I'm going to actually open up, or go to another one here. Actually, not that one. So while it's doing that, this is the exact same thing, but something that I was working on a little bit earlier. So if I wanted to do the tmin, I would work on the inputs. So in this case, I have just a few inputs. I could go and download more additional inputs, but in the interest of time, we probably will bypass that. But that would be something that we would want to do, is we want to expand the corpus of JPEGs, because 2 is really not very much at all. Actually, I think AFL has test cases. Oh, they have one, so. So I copied that there, so I added to that, so that may help a little bit. So I'm going to do my AFL tmin, and we'll do that on now we just do this one at a time, so we could actually do it on the kitty one. That would be one that we could do. Actually, let's just make this more relevant. So we're working in the in-class environment, so we'll just go and get something from in there and just grab one of these, and then our output will be the same place. Maybe do logo.min or and JPEG, and then get the application going as well. So now that I've entered the syntax of that command, it's going through and it's going to minify that one specific thing, only that one. There are a few different paths, a couple of different paths that it'll take. So in this case, right now, it's removing blocks of data that it considers to be not necessary. It'll do some character minification as well, which is really interesting. You can take a look at. I mean, you could feed it a YAML, which is a file, and it could have specific text input, and it might go and replace a lot of those characters with, instead of A, B, C, it might be 0. So it might zero out different characters, but it might preserve the structure of it otherwise. So doing the minification there, I guess I have time up there at the top. I was just kind of waiting on that. And so it's done. So if I wanted to actually to make use of this, we would need to create a bash script. A bash script, you just run the bash script once and get it to go and capture every unique item inside your input directory, whatever the input directory is. In this case, we only have 3 items because we added the not kitty to it. So let's take a look at AFL cmin and see how we can deal with that. So we can deal with in class JPEG and then our inputs. So in this case, it's a directory, and we put the outputs maybe there. Now, ideally, I'm skipping over some stuff in interest of time, so I went and minified test case. I'd want to minify everything, and once after I have completed that step, then I would do cmin on the corpus that had been minified. But in interest of time, we'll just bypass this. oh. So I need to have a new output directory. So go ahead and do that. Just make it output 2. So in this case, it narrowed it down to 3 files. You know, we could have had 1,000 and narrow it down to 500 or say, but in this case, it's already pretty minified, so we're not really adding too much to it. So let's go ahead and check out the test case, making our dictionary. Now I mentioned that was in a specific article that was so right here, and if you go and check that out, it's on GitHub. So I could just simply go and copy and paste that. And now I need to run this on the actual binary itself. So I would go to the place that it's located, because the JPEG is right there. And I'll go ahead and create the script there, testcases.sh, and just paste it in there and save it. And then I'm making an executable. And so I actually should look at what I'm creating. That would be beneficial. So it's saving it to a specific location, and that doesn't exist. So from wherever I am, it's going to do test cases string. So I must have fat fingered something there, and I may not have copied everything. That could be, I don't think it'll matter too much, but let's get the O there. So it is actually running. This is one where it doesn't display any information. We'll just see that it continues to run until it's done. Now this does take a period of time. It takes about 5-10 minutes to go through. But one thing that we could do is it's still running, and we've found all of these already that we can add and make use of. And so once we do that, then we can include our test cases. So when we actually do our command, I'll go ahead and stop this. So right now I see 428, but no crashes. I can add the X and then I can path that out to wherever my test cases are. So JPEG source, not a very good location, but I'm just kind of trying to be expedient here. So that should work now. So this gives me an error saying some test cases are too big. You can just simply remove it. It's a little bit too big. You know, we can live without it. So do in class JPEG source. No such file or directory. Louder? Oh, I see it. So now it's running with our test cases. All of these things that we do can improve the efficiency. Now, we kind of glossed through and went through things fairly quickly. A lot of this would need to occur over a period of time, maybe a period of days, several hours. Those are some of the major steps. So hopefully that gives you kind of an inkling on how to make use of AFL. We will stop here in a moment, and on Thursday we'll continue with AFL. We'll look at Peach, we'll look at our labs that are coming up, and you'll have an opportunity to make use of AFL and to create instrumented binary that you can fuzz on, maybe see if we can discover some crashes that could maybe lead to potential vulnerabilities, which is, it's at the heart of it, all of this. Sometimes we might find something in a Linux environment, but we could also may use a very similar code base in a Windows environment. There's also the Windows AFL, which is also another possibility. All right, thank you, everybody. We'll see you on Thursday. Oh, and I do have no office hours today because I have a meeting.